I want to go through a couple more examples of identifying what the hypotheses are and what the claim is. Okay, remembering that these are things that if you cannot realize these things from the scenario, then the rest of the hypothesis testing that we get into isn't going to matter. Okay, so these are the initial things that have to be conducted correctly. So, it says an educator claims that the average salary of a substitute teacher in school districts in Allegheny County, Pennsylvania, is less than $60 per day. Okay, so in that sentence, they say that we've got a claim, right? Okay, so that's obviously identifying the claim in one of our hypotheses. Now, we just have to identify what hypotheses does that go with, okay? So H sub 0 is our null hypothesis. H sub A or H sub 1 is our alternative hypothesis, okay? We're talking about average salary. So average is talking about the parameter mu, correct? Okay. If it said proportion, we'd use P. If it said variance, we'd use sigma squared and so forth. Okay, but here it says mu, or average, so we use mu. Okay, so I'm going to put those in. Now, as I continue reading that statement, the key phrase is this right here. Okay, we have to have a quantity in our hypotheses, and it says is less than 60 per day. So because of that phrase is less than, that tells you where 60 should go. Where does it go? Does it go to the null hypothesis or the alternative? When it's inequality, it goes with the alternative or the research hypothesis. So this is less than $60 per day. Okay? Now, because that phrase was identified by the claim, then we write claim with that. Does that make sense? Okay. Now, once you identify that, and sometimes it'll be this that you identify, sometimes it'll be this, but the problem is only going to generate one hypothesis. You then have to understand the relationship between the two hypotheses. They are what to one another? Complement. So what's the complement of less than 60? Greater than or equal to 60. Okay. And then all the other stuff that's in this problem is what we'll get into later today, mostly tomorrow, and next week. Okay, what we do with those values. Okay, this here has, and we'll see this in the first section or the first couple notes of 9.3 today. That talks about the level of type 1 error that we're going to be comfortable with in this problem. Okay. Number 6 here says a state executive claims that the average number of acres in western Pennsylvania state parks is less than 200 acres. Or sorry, 2,000 acres. That's very similar. My hope is that you start to see a lot of these questions are very similar. Different scenarios, okay? But we're going to have H sub 0, null hypothesis, alternative hypothesis, okay? We're talking about an average again, so mu. Okay, now it says less than 2,000 acres. Where does that go? Null hypothesis or research hypothesis? Yeah. Okay, so less than, always less than, greater than, always goes down here. There is never equality down here. So less than 2,000, that means this has to be greater than or equal to 2,000, right? Which one was the claim? You meant that one, right? First one we wrote. Okay, so H sub 1 is the claim because that is what, that's what we highlighted here. Okay, he is claiming this argument. Okay, 7 is a little bit different. 7 says the state and local taxes. The U.S. average for state and local taxes for a family of 4 is $4,172. Okay, so talking about that statement. Okay, it says is 4172. Okay, which one? When it says is, that is referring to what idea? Is that equality or is that inequality? Equality. So equality needs to go here. Is it okay? Okay. So the random sample of 20 families in a northeastern state indicates that they paid an annual amount of $45.60 with a standard deviation of 59, alpha equals 0.05. Is there sufficient evidence to conclude that they pay more than the national average? Okay. So when they say more than the national average, okay, we would be looking at the alternative hypothesis being that. Does that kind of make sense? Okay. Yes. Well, so that's what they. So when it says this, we could, because it says more than, we're going to basically do that. It's a little bit of a different scenario here, kind of. If I just do, so you say they're complements. If I do this, let's go. Okay, so if I do that, what we'll see here, and we learned this today, is that we go through, in that situation, what we call a two-tailed test. Okay, basically meaning the statistic that we come up with, the z-score that we come up with, can either be to the right or it can be to the left in the normal distribution. Okay, when we actually run through the statistics, and it could be a right or left z-score, we will know, because we'll have the data in front of us, that if it's in either one of those, the answer would be that we reject the null hypothesis. Okay, and we would then have evidence to support this. Okay, if it's in the left, we will know that it was less than. If it's above 4172, we would know it would be greater than. Does it kind of make sense? So when we say this, we're saying, okay, as long as it's on either side of 4172, we would reject this. Okay, but when we do that, we will actually have the data to say, okay, yeah, it's not equal to 4172, and when we investigate the data, we can actually see that it was to the left or that it was to the right. So when we say this, we can eventually interpret whether it's less than or greater than. Okay, but because they say, is there sufficient evidence to conclude that they pay more, we'd be looking at that to be greater than. Okay. When we want to look at the claim here, okay, because it doesn't necessarily 100% say that there is a claim or that a researcher is reporting something, okay, we will probably identify this one here as the claim. Okay, it's the pre-established hypothesis. Does this make sense on what we're doing here? It'll make a little bit more sense when I show you what we see today or tomorrow. But you won't be here tomorrow. All right. So now we're going to, there's a lot, this is what I was telling you the other day, where I was hoping you'd print this stuff up, because there's a lot of written information here that I don't want you sitting there writing down. So a lot of times when we're sitting and writing stuff down, we're not fully paying attention. We're just trying to get the words written down. What we're going to do in 9.3 is hypothesis testing, okay? Now, when we do our hypothesis testing, and this is going to be true for all of the different types of tests that we do, whether it be a z-test or a t-test or a chi-square test or whatever it may be, there's going to be two approaches, okay, two techniques. One technique is using something called critical values, and the other one is a technique called p-values, okay, or probability values. I will show you at some point, once we've learned both of them, that they are indeed actually 100% the exact same thing, okay? But I think most textbooks will introduce critical values first because it's an easier thing to understand what we're doing, but then most statistical packages will use, and most research reports using p-values. So we can't just say, well, because critical values is a little bit easier to understand, I'm always going to use that. Well, if you're using your statistical knowledge to interpret research and they don't use critical values, they use p-values, you might be lost and confused because it's not using something that you're used to. Does that make sense? So we'll do both. And eventually, once we introduce p-values, that will be the thing that kind of drives the rest of the statistical testing that we do throughout the year. All right. So it says, much like a trial, being convicted of a crime does not prove that the defendant did or did not commit the crime, right? We've talked about that, okay? Just because you've been proven guilty doesn't mean 100% that you did the crime, right? There are innocent people in jail. And just because you were not found guilty does not mean that you did not do the crime. There are guilty people that actually committed crimes that are released into the population, right? Okay. The decision that we make is based solely on evidence, okay? That's what happens in a courtroom, okay? So if, when I was growing up, one of the, the biggest court cases was O.J. Simpson, okay? Have you guys ever learned anything about O.J. Simpson? And so his ex-wife, or I don't know if they were still married or whatever, was murdered along with another guy, okay? And then O.J. wigged out and went on a driving spree in a white Bronco in California for like hours, okay? So a lot of the evidence, that kind of, and in that Bronco, I think he was with somebody, was driving, and they had firearms, and it was wild, okay? That whole thing, there's a lot of evidence amounted to saying that O.J. Simpson was guilty of this crime, okay? One of the main things, though, in the trial was that there was I think a glove found at the scene or something like that, and when he was in the courtroom, they asked him to put the glove on, and the glove did not fit him, okay? So that was main evidence that says, okay, we got all this stuff except for this glove that we found at the scene that we think was worn by the killer, does not fit O.J. Simpson. So he ended up getting acquitted for that, okay, which would mean that they did not prove him guilty. Does that make sense? Okay. Now, everybody, if you ever did they've done like 30 for 30s on ESPN for it and all that kind of, there's a lot of documentaries out there about the whole situation in the court case and all that kind of stuff, but if you were ever paying, I think I was in fifth grade. It's kind of wild because you guys had Miss Bush in fifth grade? Okay. So I had Mrs. Bush in fifth grade, and we actually stopped class that day to watch the trial and the conviction and all that kind of stuff as a fifth grader. It was wild. So that's kind of how big that event was. Everybody at the time was certain that he committed that crime, okay? But he was then, because of evidence, was not proven guilty, okay? The same thing happens with hypothesis testing. We could come up with something that think we are 100% certain that this is, we should reject this null hypothesis based on our premises, but based on our preconceived ideas, okay? But if we take a sample, and that sample, which is essentially our evidence, leads us to reject or not reject, which may be contrary to what we wanted or what we thought should happen, it is what it is. We can't do anything about that. Does that make sense? Okay. So if evidence is strong, then there is likely a conviction. So if we have evidence that is strong enough to support a null hypothesis, or evidence that's strong enough to reject it, okay, that's what we have to do. Okay. If evidence is weak, then that's going to tell us then, okay, we either need to support or reject, depending on, the strength of those outcomes, strong or weak. Does it kind of make sense? The level of evidence, and that's kind of what we try to do here with our Z-scores to determine eventually what decision to make on a hypothesis test. It says, but it does not prove it. That's what I want you to make sure you understand. When I say I'm going to reject this null hypothesis, or maybe we do not reject it, okay? Whatever the decision is, that is not proof of anything, okay? Yesterday we gave the scenario that there was this company had 20% contamination in their chickens that they were processing, okay? We could say, going through the data maybe, that we accept that or fail to reject that null hypothesis, which would mean then that they do have less than 20%. But that doesn't prove anything because they could indeed actually have more than that. We just are saying that the evidence is strong enough to not reject. Does that make sense? Okay. Another sample may tell a different story. Okay. It says, likewise, the decision to reject or not reject a null hypothesis does not prove anything. Simply states that there was strong enough evidence or weak enough evidence to go one way or the other. Okay. So the only way to prove anything statistically is to use the entire population. Okay. And what we find out then, if using the entire population will get me closer to proof or to proof, then larger sample sizes are closer to larger or the entire population, right? So maybe the larger sample that we choose, the better data, the better evidence we will be presented with. So the decision then is made on the basis of probabilities. That is when there is a large difference between the mean obtained from the sample and the hypothesized mean. So the hypothesized mean essentially is the null hypothesis. Okay? When we take a sample and we find a mean in that sample that deviates from the hypothesis mean, okay, that deviates from the established mean far enough, okay, then we will be able to either reject or not reject based on that, right? Does that make sense? Okay. So if let's say that the average height of 17-year-olds is 5 feet 8 inches. Okay, I take a sample and I find that the sample has a mean height of 5 feet 7.5 inches. Okay, I would argue probably that data is not far enough away from 5 feet 8 inches to reject that the mean of 17-year-olds is 5 feet 8 inches. Does that make sense? But if I took a sample of individual 17-year-olds and I find that their average is 5 feet 1 inch, okay, maybe that 6 inches, 7 inch difference from the hypothesized mean is enough to say no, the population mean is not 5 feet 8 inches, or I cannot accept that it's 5 feet 8 inches. Does that make sense? Okay, so it's all about how far the difference is between the hypothesized mean and the mean of our sample. So the question is, how large a difference is necessary to reject the null hypothesis? And that is all based on our level of significance. Our level of significance is identified by alpha. Okay? You guys remember alpha being so we have a confidence level of like 95%, right? You guys remember doing alpha and alpha over 2? Okay? Same thing here. Okay? It's the exact same value. So if my confidence interval is 95%, alpha is 5%. Okay? Which means, that's called the level of significance. In our situation, it's the maximum probability of committing a type 1 error. So if I have 95% confidence level, okay, then I have a 5% level of significance, which is the same thing as saying that I have 5% probability of committing a type 1 error. Okay? We said the probability is symbolized by alpha, okay, and this is usually the way you would write it as kind of a definition. Now, I talked about this yesterday. I don't like, because I can't remember it for the life of me for whatever reason. This thing here, okay. Did you say dementia? All right. So this is I mess this up all the time. Okay. So this is what I use. Okay. RAAR, right? Okay. It's palindrome. Okay. 4 letters. Split it in half. Okay. When you split it in half, you got a first half and you got a second half. Correct? The first half is referring to type 1 error right here. Second half is referring to type 2 error. That's pretty logical. Would you argue with that? Okay? Now, the RA, what that stands for is that you reject a null hypothesis that you should have accepted. Reject something you should have accepted. Okay? And if you look right here, okay, H sub 0 is true. So when H sub 0 is in actuality true, we should accept it, right? Okay? Or I guess we never really say accept. So when I say accept here, it's equivalent to the statement fail to reject, right? Okay? So if it's true, we should accept it. Okay? But if we rejected it, the intersection of those is type 1 error, right? So type 1 error is rejecting something you should have accepted. Okay? Type 2 error is accepting something that you should have rejected. Does that make sense? Okay? And you see here type 2 error. Okay? We accepted it, do not reject, so that's accepting, but it was false, so we should have rejected. This is what we want to minimize. Okay? We want to minimize type 1 error is when you reject something that should have been accepted. Okay? It says the probability of type 2 error is symbolized by the Greek letter beta. Okay? We don't deal too much with beta, or at least right now. Okay? It says in most hypothesis testing situations, beta cannot easily be computed. Okay? However, alpha and beta are indirectly proportional. As one increases, the other one decreases. Okay? So we talked about the seriousness of type 1 and type 2 errors yesterday in specific scenarios, right? In those scenarios, they didn't have any data with them. One was like Frank thinks his climbing equipment is safe when it really isn't, or something like that. Okay? So what do we mean by indirectly proportional? Anybody know what that means? Sometimes maybe in Algebra 1 you refer to it as they are disjoint or disjointly related. Just remember direct variation. What's direct variation? Okay, so you're in the right train of thought here. So direct variation or joint variation means that when one increases, the other one increases. Okay, so when we did that in Algebra 1, that was the first type of line that you dealt with. Okay, we graphed like something like y equals like 2/3 x. Okay, so you go through 0, 0. As the x increases, the y increases. So that's called joint variation, or they increase proportionally. Okay, indirect proportion, okay, or disjoint relationships, okay, means that as one increases, the other one decreases. Okay, or as one decreases, the other one increases. So if we want to decrease type 1 error, that will ultimately increase type 2 error. Does that make sense? Okay, but you see here, and this is all like intro to statistics courses, we'll have this kind of notice that, you know, even though there is a probability attached to type 2 error, it's something outside the scope of an introductory stats class. Okay, so we won't deal with it very much, if at all. So statisticians generally agree on using 3 arbitrary significance levels: 10%, 5%, and 1%. Okay, but you can use anything that you want. If you want to use 13%, have at it. Okay, it's just not very common or maybe even practical. Okay, because those then relate to 90% confidence level, 95% confidence level, and 99% confidence levels. Okay, it says if the null hypothesis is rejected, then the probability of type 1 error would be 10%, 5%, or 1%. Okay, so that's when we reject something. Okay, if the null hypothesis is rejected, okay, then type 1 error, reject something that we should have accepted, is 10%, 5%, or 1%. Okay, and theoretically, we probably want that type 1 error to be smaller, right? Okay, we don't want. It would kind of make no sense to do something where we choose alpha to be like 50%. Okay, because then you're right on the fence and doesn't make a whole lot of sense for our practices. There will be situations though that we'll say, okay, we should have at, and I think I said this yesterday, at maybe 10% we reject the null hypothesis or accept it. Okay, but at 5% we do the opposite. Okay, and we'll see some examples. We'll do some deliberate examples like that. We'll adjust alpha and see if that changes our decisions. Okay, because that can happen. What happens a lot of times, this is why we talk about p-values, is that statisticians will ultimately a lot of times collect the data. They will process the data. They will tell you what the z-scores are and all that kind of stuff. And then they won't make a decision of reject or not reject, because they will then say, okay, now that I've given you the p-value, you make the decision on the alpha that you want, and then make the decision about rejecting or not rejecting per that alpha. Okay, and that's kind of a, I don't want to say a safe thing, but it's generally a practice because of the idea that you can reject at one level but not reject at another level. That's why statisticians do that. So there's alternative ways of thinking. When alpha is 10%, there is a 10% chance of rejecting a true null hypothesis. That's what type 1 error is. Okay. So statisticians do not have to use these levels of significance, and it is their choice. Usually the choice is dictated by the context of the study and the seriousness of type 1 error. Okay. So they will go through and say, okay, scenario-wise, how bad is type 1 error? Okay. If we were to commit type 1 error, does that put people in danger by them abiding by our research? Okay. And then that will help them decide what alpha to use. One thing that we need to understand is that, so when I'm doing research, okay, I might be a person, and this is all about talking about the ethics of statistics. When I'm doing research, I probably have somewhat an invested interest in the outcome of that research. Would you guys agree with that? Okay. Maybe I'm doing research, doing research on like maybe an instructional strategy that I like to use, and it's my favorite instructional strategy. And I don't want research to show that that strategy sucks, because then I have to stop using it, right? Okay. So I might go through collecting data and all that kind of stuff, and the data might show that strategy stinks at that alpha level. But if I change the alpha level, it might tell me my strategy doesn't suck. Does that kind of make sense? Okay. Would you think that's unethical? Yeah. Okay. If we go back to that contamination question about the chickens yesterday, okay, if we at one alpha level say, no, there is no contamination, okay, we cannot, we do not reject the null hypothesis. But maybe I've got some connection to that plant. Maybe they fired me recently, okay. And then I can say, well, okay, let's change the alpha level. And now if I change the alpha level, then it might say accept or reject the null hypothesis, okay, whichever one it might have been, to say that the company is indeed violating the law. Does that make sense? So that the whole thing about ethics starts to come back into play here. So one thing we need to understand, we'll talk about this again later, I think I have it in section 9.4 maybe, that once a alpha level is chosen, you do not ever go back and change it, okay? A lot of stuff is done preliminary. You make decisions preliminary, and then you let the data tell the story, okay? As we do this, there's going to be some terminology again, that we are not familiar with, okay? First one's critical value, okay, a lot of times abbreviated C.V. So after choosing a level of significance, a critical value is determined using a table, and the value establishes where I've got some wording there messed up. The critical value establishes regions, okay, underneath our normal curve, that we call critical and non-critical regions. And they are they're directly related to like alpha over 2. Can you remember doing confidence levels of 95% in the middle? And then we had, 2.5% to the left, 2.5% to the right. Okay, those alpha over 2 regions can and will be critical regions for us when we work through these testings. Okay, the critical region, sometimes referred to as the rejection region, is the range of values of the test value that indicates that there is a significant difference between the data in the sample and the null hypothesis. Okay? And it suggests then that the null hypothesis should be rejected. Okay? Does that make sense? So we'll take on all these, we'll draw a picture. We will do the calculations to identify the critical regions. Then we'll take our sample data. We'll do the calculations on that, and that calculation we can then fit into our normal distribution. And if it lands in the already predefined critical regions, then that tells us you reject the null hypothesis. Okay? If it does not fall in the critical region, then it falls in the non-critical region, which in the non-critical region, that is where you fail to reject the null hypothesis. Okay? It's the range of values of the test value that indicates that the difference was probably due to chance. Okay, so our sample then, we've talked about this, the sample mean will never be identical to the population mean, right? Okay, it's always going to be off a little bit. But it's off a little bit because the sample is never 100% the same as the population, right? Okay, so there's going to be a difference between the sample mean and the population mean. If that sample mean deviates enough, okay, then we can reject the null hypothesis. If it doesn't differ enough, then we would fail to reject the null hypothesis. Okay, but that difference that exists, if we fail to reject the null hypothesis, just happened because of chance. Okay, because of the individuals or the components that chose it in that sample. Okay. Says critical values can be found on either side of the mean, and it is directly related to the alternative hypothesis. Okay. Remember, the alternative hypothesis has an inequality sign in it, right? Okay. If the inequality sign, so this is when we establish that our parameter is written first. Okay. So I always want to write in my hypotheses mu less than, greater than, or not equal to. Does that make sense? Okay. Because the direction of the inequality then tells me what type of test we're using. Okay. If it's a greater than sign, so if it says mu is greater than in my alternative hypothesis, that's called a right-tailed test. And what that means is that our critical region, which will be the region that tells me to reject a null hypothesis, will be to the right of the mean. It'll be a right-tailed test. Okay. So when we look at, we'll just draw a quick normal distribution here. Okay. Here's our mean. And that mean right there is our hypothesized mean. That's the null hypothesis. Okay. The critical region, if in a right-tailed test, would be this area over here. Does that make sense? Okay. That area over there is the critical region. And if I run through the calculation, we'll find a z-score. We're going to standardize a score here in a little bit. If my data lands over here, that tells me that my sample mean was far enough away from the hypothesized mean that would lead me to the conclusion to reject this as the actual population mean. Okay? So a right-tailed test, we're looking at an area that is to the right of our mean. And that was a greater than sign. So a left-tailed test, what do you think a left-tailed test is? Yeah, so a left-tailed test, the image you're going to look at here, you got your mean, which is established in H sub 0, and a left-tailed test will be an area over there, okay? So those that shaded region that I'm coloring there is referred to as the critical region, okay? And we're going to find that through understanding what we chose for alpha, okay? But that'll be my critical region. And then the white area is my non-critical region. So if I run through a sample statistic, okay, z-score, and it lands in the green, what I'll do is I'll reject the null hypothesis because it's far away. It's enough evidence, it's strong enough evidence to say that your sample mean is different from the population mean by enough to say that the population mean that was hypothesized is not true. Okay, if it lands in the white, then you're going to say, well, our sample statistic is not different enough from the mean to say that the mean was not what was hypothesized in the null hypothesis. Okay, and it says that, when it falls in the white, basically it's that the difference that is recognized in the sample was simply due to chance and not because the actual population mean is different than what was hypothesized. Okay, so those are called one-tailed tests. Okay, this is kind of the way, you guys remember, and I'm not going to use, I've got it written here, I'm not going to ask you guys to use a table. I think we've used the calculator enough that we can gain these probabilities from our calculator using the normal distribution commands. But it says how to find critical values for alpha equals 0.01. Okay, it's the right-tailed test. Okay, so what we do is we look through so alpha to the right, okay, that's 0.1, 0.01. So this shaded region, the shaded area, is equivalent to alpha. Does that make sense? Okay. Now, because this table and because our normal distribution command on our calculator is left-tailed, okay, cumulative from the left. So this 0.9901 that we're seeing here in this table, and that's exactly what you would get on your calculator if you typed in normal.dist and then filled in the components. Okay, so I'm talking Excel, and we'll do it here in a little bit. We would type in, so if I typed in I guess what I'm saying is to get this number of 2.3 or 2.33, which is that z-score, I would have to type in this white area. Does that make sense? So to find that white area. So that's why we're taking 0.1, okay, and looking then for essentially its complement of 0.99 in the table. Okay. Another way of doing it is actually, and I think this is what we'll do on our calculator, is if I type in 0.01 on my normal distribution, it's actually going to give me the z-score over here on the left. But what do we know about that z-score there on the left compared to this one because of the symmetry of a normal distribution? They're the same, except for this one here is going to be what? Negative. Okay. So once I find that one, if I know it's a right-tailed test, I'm just going to take the positive version of it, and it'll give me that z-score. Does that make sense? Okay. Then what we do, that establishes our critical region. Okay. The next thing we'll do is we'll take our sample data. We'll take our sample data and we will conduct a z-score on the sample data. X minus mu over sigma divided by square root n. That's how we standardize sample data. And if that value that I get from my sample is a z-score over here, okay, which is in my critical region, then we will reject our null hypothesis. If it's over here or over here, anywhere in the white, then we would fail to reject our null hypothesis. Okay, so that's a right-tailed test. And again, just trying to give you the overall understanding of what's going on. We will then eventually, as we see some examples, do all of these steps with specifics. Okay, this would be a left-tailed test. Okay, so here you see with still alpha being 0.01, you see now that we get the same negative 2.33. So we're going to use that relationship to help us out a little bit, that the symmetry exists in a normal distribution. But if now our z-score for our sample data would fall in the yellow there, we would reject. If it falls in the white, we would fail to reject. Okay. So it can also use inverse normal functions with software to identify these critical values. That's what we're going to do. Okay. So we'll start with that tomorrow. A two-tailed test, just real quick. A two-tailed test basically is the one that when our alternative hypothesis has the not equal to sign, so the equality sign with a slash through it. When we say that, we're not establishing whether we should be to the right or to the left. We're establishing that it's just different from the hypothesized mean. So it could be to the right or to the left. So what that happens then is if my alpha level is 10% or 1% or whatever, then the critical regions are established by using half of that alpha in the left tail and half of that alpha in the right tail. Okay, so here at 1% is my alpha. Then this region here in a two-tailed test would be half of that, so 0.005, and this would be 0.005. Okay. Then what happens when we find the z-score of our sample data? If it falls in either of those, then we would say that we are far enough away from the hypothesized mean to reject the null hypothesis. Okay. And as that first question that Blaise said was confusing at the beginning when we were establishing the hypotheses, and I did not use a not equal to sign, is because once I run the sample data and I find that it falls in this critical region here, okay, and I reject the null hypothesis, well, because it's to the right of the mean, it tells me it was more than. Does that make sense? Okay, and if it was to the left of the mean here and I reject it, then it tells me that it was less than. So even though a two-tailed test has two regions that I can reject from, I will still know which region caused the rejection, either to the right or to the left. So I will know more than or less than as we do this. Okay, and we'll investigate that, talk about that in specific examples as well. Is that okay with everybody? Okay. There are some things that you guys can memorize. We'll start about this tomorrow. There are critical values that we can memorize, but I also want to give you the procedure for finding them. We've done it with our calculator. You guys remember, like 95% confidence level was 1.96, right? That was the z-score we used. It's the same thing here. Okay. So we'll get into that tomorrow, and we'll hopefully get some preliminary examples done with this as well.